Let's look at this technique of integration by substitution. We talked a little bit about it in some of our earlier topics. A lot of the times it's annoying, to be honest, because in 3-Unit what happens is they give you the substitution to use. And so you don't have a choice. If they tell you to use a particular substitution, you have to do it that way. But you might look at the integral and go, oh, hang on, well, that's obvious because it's just a derivative times some function to the power of n. And you might see it straight away. But if they've told you to use a substitution, then you have to use the substitution. Now, if they don't mention it, then it's completely up to you how you go and solve it. What we're basically trying to do is to convert it into one of the standard integrals. Now, what are the standard integrals? Okay. The old standard integrals that used to appear in the HSC prior to this year, because this year is when they've changed it to a reference sheet that you'll be getting. But these are the old ones that used to appear, and we'll probably put this in our Extension 2 assessment task on integration. We'll probably still give you the old one, I think, when we do that. I think that's going to be the plan anyway. So it started off with a basic one. Oh, look, if you integrate a polynomial, you add 1 to the power over the power. This sort of stuff is just technical to, because n can't equal -1 because you can't have 0 on the bottom of the fraction. X can't equal 0 if n is less than 0 because you can't have 0 on the bottom of the fraction. That's all that's there for. Then we saw the 1 over x situation, which is our log derivative on function. Then they gave us the e to a linear power, 1 over a e to the ax. And then our trig functions, cos, of course, went to 1 on a sine. Sine went to -1 on a cos. Sec squared, 1 on a tan. This was the interesting one. That was there, I guess, for conics in 4-Unit, because we needed to know how to differentiate sec. So, but they put it in the form of an integral. So the integral of sec tan was sec. Then there was the inverse trig ones. They gave us those. So 1 on a squared x squared, inverse tan. And there's our, well, they quote it as inverse sine, but of course it could be minus the inverse cos. And then they gave us these two integrals, which again is to do with 4-Unit integration they come up with later. But they were the standard integrals that they gave us. All right, the new standard integrals. What do they give us now? And in the handouts, I have put a copy of the new resource sheet in there. It's mixed up. They're not all together. So in the mathematics section, this is how they write it. So now, instead of just going x to the n, they write linear function to the n. But it's still add 1 to the power over the power, but of course reminding you to multiply by the coefficient of x. The exponential's still there, but notice instead of just ax, it's now ax plus b. Still the same thing. Instead of just going 1 over x, the sheet now actually says derivative over function is the log of the absolute value. Because remember, technically it was absolute value of the function, because you can't find the log of a negative number. And then there's the sine ones were there, cosine, and sec squared. Okay. So they're the ones you find amongst the 2-Unit ones. But then, in a separate section, so the resources for maths extension 1, you find these ones. And there's your inverse trig. So you've got the inverse sine of x on a, and the inverse tan of x on a, and they're the only integrals that gives you. And there is no resource sheet for extension 2. No longer listed. That was the one that's useful for conics, and then say, those two log ones, they're not there anymore. So whether that means we're never going to get a question where we have to integrate something, I don't think that's what it means. But the non-standard integrals, I call these the non-standard integrals because they're not given to you. But look, if you know how to integrate something, you don't waste time. If you know what the standard integral is, you just use it. So ones that crop up very often, especially in our 4-Unit ones, we'll see this one, you end up with a situation of du on root u or dx on root x. And so that's 2 root u. So du on root u, integrate it, you get 2 root u. Du on u squared is another common one that comes up a lot in the 4-Unit work. And that's just minus 1 on u. Integral of log. Remember when we did logs, we didn't actually integrate log? Turns out the integral of log is x log x minus x. So again, if you just remember that one, you don't have to worry about playing around and trying to work it out. Oh yes, integral of log x minus x. Integral of tan. Remember we could rewrite tan as sine on cos and do it that way. Ends up being the log of sec or minus the log of cos. And then this idea, the integral of a complementary trig ratio will equal minus the complement of the answer. So if you know how to integrate a trig ratio, then you know how to integrate its complement. So integrate sec squared you get. So therefore, when you integrate cosec squared, which is complementary of sec, you get minus cot. So minus the complement of the answer. The answer for sec squared was tan. So for cosec squared, it's minus cot. All right? So here we go. We'll try this one. Integral of cot. Well, what did I say the integral of tan was? Log of sec. Therefore, the integral of cot will be minus the log of cosec. So it was the log of sec for tan. We change it to minus, or whatever sign's out the front. So in this case, we change it to minus. And the trig, we turn to its complement. And you might prefer to write that as the log of sine if you don't like the negatives out the front. All right, let's have a look at this idea of integration by substitution. So this is what I say where it's real annoying. If you were just to give me that question there, I'd look at that and say, well, hang on, that's just a situation of derivative times function to a power. Because I've got x squared plus 4 to the power of a half, and I know the derivative of x squared plus 4 is 2x, and I've got x there. And so I could do it really quickly, but sometimes they're very annoying, and they say, use u equals x squared plus 4. Okay. Now, for in it, they don't give you the substitution, so that's why I've written this little thing here. If you do want to use substitution, then usually you make what's causing the problem u. And what's causing the problem here is the square root sign, because I can't expand out the square root sign. So I'll make u equal to x squared plus 4. Now, if u is x squared plus 4, then du is 2x dx. Yep. This is that idea of separating the variables. Remember how I did that when we were doing the motion questions? So instead of writing it as du dx is 2x, I've separated it and made sure the x's are together and the u's are together. So it's just du is 2x dx. The advantage of doing that is over here now, I see I've got x dx. Well, hang on, x dx, that's half of du. So I can now rewrite this integral as a half u to the half. And u to the half's just a standard thing, just add 1 to the power over the power. So 2/3 u to the 3 on 2. And so that's 1/3 u 3 on 2 plus, of course, a constant. But then I can substitute back in, because the original question was in terms of x. So my answer there should be in terms of x. Well, that would be a mere mortal answer, of course. Can't help myself. There we go. X squared plus 4 root x squared plus 4. Okay. So if you have to pick a substitution, go for the thing that's causing the problem there. So another way I could do this, if you have a look at the root and you see it's the sum or difference of two squares, and x squared plus 4, of course, is the sum of two squares, you might try a trig substitution and try and create a trig identity under the square root sign. Now, that's useful for the root, because if you can create a trig identity, you can turn the two terms into one term, and the trig identity is usually something squared, and so then you can get the square root of something squared. So x squared plus 4, think of your trig identities. Which trig identity had a number plus something squared? I'm going to make x equal to 2 tan theta. Dx then is 2 sec squared to theta. So let's substitute in. Now let's look at that closely, what I've substituted in for. Out the front, I had x. So that became 2 tan theta. Underneath the square root sign, I had x squared plus 4. So that becomes 4 tan squared theta plus 4. But then I've also got this dx. Well, dx becomes 2 sec squared theta to theta. That tidies up. It might look really ugly at the moment, but remember, 4 tan squared plus 4 is 4 sec squared. The square root of 4 sec squared is 2 sec times 2 sec squared is 4 sec cubed. Multiply that by the 2 tan theta, and I now have 8 integral tan theta sec cubed theta. Ooh, forgot my d theta. Should be a d theta there, of course. Now, I didn't necessarily say this was going to be an easier way of doing this question. I'm just saying this is an alternative way of doing this question, because now I've got this problem of tan theta sec cubed. I'm going to change everything to sine and coses, because look what happens. Tan becomes sine on cos. Sec cubed becomes 1 on sec cubed. Sorry, 1 on cos cubed. So I end up with sine theta on cos to the power of 4. I've now got something I can integrate. Because if I do another substitution, if I now say u equals cos theta, then du is minus sine theta to theta, and I end up with minus du on u to the power of 4. Well, that's just u to the negative 4. Add 1 to the power over the power. So I've got minus a third u to the minus 3. There we go. 8 thirds sec cubed, because u is cos u, and the reciprocal of cos is sec. And so I actually end up with that. Hang on. That's in terms of theta. I want it now in terms of x. Oh my gosh. How am I going to get x into this? It's all right, because what do I know? I know x is 2 tan theta. So if I draw myself up a little triangle, x is 2 tan theta. In other words, tan theta is x on 2. The hypotenuse becomes the square root of x squared plus 4. Now I can substitute in for sec theta, which would be hypotenuse over adjacent. And I have 1/3 the square root of x squared plus 4 on 3. That's just a mere mortal answer. So there we go. And we get exactly the same answer. Possibly not the best substitution to use. So let me just recap on that particular example. In 3 unit, they're going to give you the substitution, and they would definitely give you the first substitution, not the second substitution. They would say use u equal x squared plus 4. But this just illustrates is that there are different ways of solving the same problem, but different substitutions. Whilst this was not a good method for this particular question, it could be a great method for other questions. It just depends how we go. Remember, always keep an eye out for that derivative times function, because if they're not saying use substitution and you spot that derivative times function straight away, you're going to save yourself a lot of time. All right, let's have a look at this one. X plus 1 on 4x squared plus 8x minus 7. When I look at something like this, I see a polynomial and a polynomial. And when I see that, I'm looking at the degree of the polynomial. The degree on top is 1, the degree on the bottom is 2. So I'm thinking log function. And the reason I'm thinking log function, remember logs, derivative on function. Whenever you differentiate a polynomial, the degree goes down by 1. So if I notice the numerator, the degree is 1 less than the denominator, I'm thinking log function. Now, if that's the case, the substitution I want to use is going to be the bottom of the fraction. So hopefully they tell me to use u equals 4x squared plus 8x minus 7. And if they do that, differentiate, I get 8x plus 8. Well, have a look. The top is x plus 1. I can easily turn that into 8x plus 8 by multiplying by 8. So it becomes 1/8 of just du on u. Du on u, log u. So it's 1/8 log u. Substitute the u back in. There's our answer. So if you notice polynomial on polynomial, look for that derivative on function. Can I create the derivative on top? Okay, what's causing the problem here? Yep, I'd agree. I'd say it's the log x that's causing the problem. So again, hopefully that's what they're going to tell me to use. U equals log x. So the derivative becomes, or du becomes dx on x. And have a look, we've actually got that there. Dx on x. There's the du. So we've got du on u cubed, which is u to the minus 3. Add 1 to the power over the power. We get minus 1 on 2u squared. Substitute the u back in, and we've got log x squared on the bottom. X on the square root of 1 minus x. What's causing the problem? Like if you had to pick something there, we're going to substitute. What would you pick? 1 minus x? That would seem sensible. It's underneath the square root sign. Still got an x on top, but that's okay. We can deal with that. What did they give me? Sometimes their substitution, instead of quoting it as u equals, they'll quote it as x equals. And have a look what they've done with this one. 1 minus x was a good guess, and you could do it with 1 minus x. But actually a better one to do is to make u equal to the whole of the denominator. U equals the square root of 1 minus x. Or another way of saying that, x equals 1 minus u squared. If you make x equal 1 minus u squared, and then dx will be minus 2 du, and we'll just substitute in. So what I'm saying is, substituting the u equals function x instead of x equals function u. The advantage of doing that is later on, if it becomes a definite integral, it solves any problems we might have with the domain. And you go, oh, hang on, you can't substitute that number in, and things like that. So we end up with 1 minus u squared over u, but then the dx is minus 2u du. So the u's will cancel. I end up with 2 lots of the integral of u squared minus 1. Add 1 to the power over the power, so that's u cubed minus u. Substitute back in. U is the square root of 1 minus x. Oh, I can't leave it like that. I mean, that probably will get you the marks, but come on. Mere mortal. So much better. 1 minus x root 1 minus x minus 2 root 1 minus x plus a constant. So if they give us the substitution x equals, then to the side I usually rewrite that as u equals, so I know what I'm substituting back in later on. This is one of the ones where I get annoyed. Because I'm looking at that, I don't know if you're looking at it and seeing the same thing, but the derivative of sine is cos. So it's in the form derivative times that. So if they tell me a substitution to use, u equals sine x, du will be cos x. Now, this is a definite integral. So I can't use these numbers in my new integral, because my new integral I'm going to write will be in terms of u, not in terms of x. These limits are for x. So I need to work out what the new limits will be. But I've got a formula over here. U is sine x. So when x is pi on 3, u will be sine pi on 3, which is root 3 on 2. And when x is pi on 2, u will be sine pi on 2, which is 1. So my new integral, the limits will become root 3 on 2 to 1. And we're just integrating u to the power of 5 to u. Add 1 to the power over the power. The advantage with a definite integral, I don't have to substitute back, because I just am coming up with a value, substituting my new limits, and I get the answer straight away. So 37 on 384 for that one. X dx on the square root of 25 minus x squared. What would you use for the substitution here? No cheating and looking at the sheet. What's causing the problem? Yep, so u equals 25 minus x squared, could be. But then remember, we had that other one where they made the whole square root the substitution. They said, why don't we make root 25 minus x squared be u? Or, there was the other idea I showed you. Difference of two squares there. I could do a trig identity, change it into a trig one. Which way did they go? Let's see. They've decided to go with just the simple u equals 25 minus x squared. All right. U equals 25 minus x squared. Du is minus 2x. It's a definite integral. We've got to work out our new limits. When x is 3, u is 16. X is 4, u is 9. So substituting in, we get minus a half du on root u. There it is. Remember I said these common ones that pop up a lot? Du on root u. Oh, 16, 9. The bigger number's down the bottom. It's fine. It's allowed to be there. It just means you would substitute 9 in first, substitute 16 in second. If you're unhappy with that, you can swap them round, but change the sign. Notice I changed it to positive half. So if you're uncomfortable with the bigger number being down bottom, it's fine. Just swap them. But change the sign. Okay, u to the minus a half, u to the half. This is what I'm saying. If you remember, du on root u is 2 root u. You could have gone straight to this step because 2 times a half is 1. We just have the square root of 16 minus the square root of 9, which is just 1 for this one. Interesting. Same square roots, but this time it's not in a fraction. So again, we have those choices. We could make u equal 25 minus x squared like we did the last one. We could make it the whole of the square root. Or we could do a difference of two squares. In this one, I'm not going to choose u equal 25 minus x squared. Why? Sorry, say again? Yeah. Did everyone hear that? Or what we're saying there is, because remember, we're going to say u equals 25 minus x squared, which means when we differentiate it, du will be minus 2x dx. How am I going to get that into this problem? There's no x dx there. So that would be a bad choice. Square root of 25 minus x squared would cause similar problems. So x equals 5 sine u. In other words, u is the inverse sine of x on 5. But dx is 5 cos u du. Let's have a look at our limits. When x is equal to 0, use the inverse sine of 0, which is 0. X is equal to 5, use the inverse sine of 1, pi on 2. 0 to pi on 2, square root of 25 minus 25 sine squared, times 5 cos u du. But square root of 25 minus 25 sine squared. 25 minus 25 sine squared is 25 cos squared. The square root of 25 cos squared is 5 cos. So I've got 5 cos u times 5 cos u, which is 25, there we go, 25 cos squared. Integrate cos squared. Oh, we need another trig identity. Cos squared is the same as. All right. Half of 1 plus cos. So half of 1 plus cos 2u. Now we can integrate u plus a half sine 2u. Substitute pi on 2. Substitute in 0. 25 pi on 4. Now, if you're going to do this by substitution, that is the best substitution to use, even though there's a fair bit of working out. Problem is, I wouldn't use substitution. Here's the question. Square root of 25 minus x squared. I recognise that shape. It's a semicircle. What's integration? Area. So the area from 0 to 5, that'd just be a quarter of that circle. So quarter pi r squared, 25 pi on 4. A little bit quicker than doing the substitution. So if you do, remember, the whole idea of integration is to find the area under strange shapes, irregular shapes. If it's a shape you know, a triangle, a circle, a square, a rectangle, just find the area of the rectangle, the area of the square, whatever it happens to be. Don't forget algebraic manipulation. Dun, 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 dun. Look at this one. X cubed root 4 minus x squared dx. oh, I think you're going to enjoy this one. I could rewrite that. You like that? What I've actually done is I've added 4x and I've subtracted 4x. Why on earth did I do that? Because I can now write this bit as x times 4 minus x squared, which happens to match the 4 minus x squared under the square root sign. So I could now change that into two integrals. X outside of 4 minus x squared to the power of 3 on 2, 4x outside of 4 minus x squared to the power of a half. The derivative of 4 minus x squared is minus 2x. I've got it in the form derivative times function, so I can just integrate it. Add 1 to the power over the power. Now, well done if you spotted that straight away. That takes a little bit of practice and doing a few exercises to get used to that one. Definitely no one in TUNIT would ever think about that. Probably not even extension 1. And you'd have to be pretty good in extension 2 to spot that one straight away, to try that algebraic manipulation. But don't worry, we're going to be doing a lot of integration. So, okay. I said we're going to do a lot of integration. There's a lot of integration.